Operations on power series. In this video we're going to discuss the various different types of power series which can arise from adding, subtracting and multiplying two power series. We'll discuss finding the radius of convergence of a linear combination of power series. We'll also discuss how to find a power series representation of a function as a combination of power series. Finally, we'll discuss what happens when we multiply two power series together. To answer these questions about power series, let's consider what we already know about regular series. If we have two series, the sum over n of an and the sum over n of bn, which converge, and we have a constant c, then we know the sum over n of an plus the sum over n of bn is equal to the sum over n of an plus bn, and we also know that this will converge. Similarly, since c is a constant, we know when we're summing over n, c multiplied by an, we can take the constant of c outside our sum. This gives us c multiplied by the sum over n of an, and this also converges. Now we want to ask the question, what would have happened if instead of being given regular series, we were given power series? We recall, when we're discussing power series, they don't converge or diverge, instead they have what we call a radius of convergence. This is because x is a variable, so for each value of x we'll have a different power series, and we want to know the values of x for which these series converges. So let's add radius of convergences for both of our power series. Let's call these R1 and R2. We now want to know what happens when we try to add our power series together. We'll do this by using our formula for adding two series together. We're trying to add two series together. The summand in the first one is an multiplied by x to the nth power, and the summand of the second one is bn multiplied by x to the nth power. And our formula tells us that when these series converges, we can just add the summands together. So for any value of x which both of our power series converge, we can use this formula. This gives us the sum over n of an multiplied by x to the nth power plus bn multiplied by x to the nth power. And we can factor out x to the nth power. This gives us the sum over an of an plus bn multiplied by x to the nth power. We notice in particular that this new formula will always work when the absolute value of x is less than the smaller of r1 and r2. This is because if the absolute value of x is less than the smaller of r1 and r2, then it's smaller than both of them, so both of our power series will converge. We might be tempted at this point to call the smaller of R1 and R2 the radius of convergence for the sum of our two power series. However, this is not necessarily the case. To see why finding the radius of convergence of this series is not so simple, consider the following example. The sum over n of x to the nth power divided by n will converge when the absolute value of x is less than 1. Similarly, the sum over n of negative x to the nth power over n will also converge when the absolute value of x is less than 1. However, adding these two power series together gives us the sum of 1 over n minus 1 over n multiplied by x to the nth power, which simplifies to just give us the sum over n of 0, which converges for all values of x. So we can use this formula to add any two power series together. However, we're going to have to work hard to find the radius of convergence of our new power series. We'll have to use techniques such as inspection, the ratio test, or the integral test to find our new radius of convergence. Let's take a look at an example. Suppose the sum from n equals 0 to infinity of an multiplied by x to the nth power is a power series whose interval of convergence is the open interval from negative 3 to 3, and the sum from n equals 0 to infinity of bn multiplied by x to the nth power is a power series whose interval of convergence is the open interval from negative 5 to 5. Find the interval of convergence of the series, the sum from n equals 0 to infinity of anx to the nth power minus bnx to the nth power, and find the series of convergence of the series, the sum from n equals 0 to infinity of bn 2 to the nth power x to the nth power. The question wants us to find the interval of convergence for two different power series. We recall that an interval of convergence is an interval which contains all values of x such that our series converges. If both power series converges, so the absolute value of x is less than the smaller of 3 or 5, therefore, since we're adding together two convergent power series, we can combine the summands just as we would in a regular series. This gives us the sum from n equals 0 to infinity of anx to the nth power minus bnx to the nth power will converge when the absolute value of x is less than the smaller of 3 and 5. So we've shown that the power series converges when the absolute value of x is less than 3, but what about when it's equal to 3? What about when it's greater than 3? Let's consider the case when the absolute value of x is equal to 3, and let's assume that our series converges. Then, since the absolute value of x is equal to 3, the sum from n equals 0 to infinity of bnx to the nth power must also converge, because its radius of convergence is 5. Now, what would happen if we tried to add these two series together? Well, we've assumed that our first power series will converge when the absolute value of x is equal to 3. And if the absolute value of x is equal to 3, this is less than 5, so our second power series must also converge. This means we're trying to add together two power series which both converge, so we can just add the coefficients of x to the nth power together. We see that negative bn and bn cancel. So this simplifies to give us the sum from n equals 0 to infinity of an multiplied by x to the nth power. However, the sum from n equals 0 to infinity of an x to the nth power will only converge when the absolute value of x is less than 3, so this series must diverge. The only way this could have happened is if the sum over n of an x to the nth power minus bn x to the nth power was divergent when the absolute value of x was equal to 3. Therefore, since neither 3 nor negative 3 are in our interval of convergence, we've shown that the sum from n equals 0 to infinity of an x to the nth power minus bn x to the nth power has the interval of convergence, the open interval, from negative 3 to 3. So let's clear some space and work on the second case of finding our interval of convergence. We'll let the function f of x be equal to the sum from n equals 0 to infinity of bn x to the nth power, and this will be true whenever the absolute value of x is less than 5. We want to make this power series look like the one given to us in the question. We'll start by multiplying and dividing our summand by 2 to the nth power. Next, we can use our laws of exponents to notice that a half to the nth power multiplied by x to the nth power is equal to x over 2 all raised to the nth power. We want our summands to have x to the nth power instead of x over 2 to the nth power, so we'll let u be equal to x divided by 2. This gives us that the sum from n equals 0 to infinity of bn 2 to the nth power multiplied by u to the nth power will converge when the absolute value of 2u is less than 5. If the absolute value of 2u is less than 5, this is the same as saying the absolute value of u is less than 5 over 2. So we've shown that the radius of convergence of the sum from n equals 0 to infinity of bn multiplied by 2 to the nth power multiplied by u to the nth power is 5 over 2. Since it doesn't matter if we call our variable u or x, we've shown that our second power series, the sum from n equals 0 to infinity of bn 2 to the nth power x to the nth power, will have the interval of convergence, the open interval, from negative 5 over 2 to 5 over 2. Let's now take a look at what would happen if we tried to multiply two power series together. So let's say we wanted to multiply two power series together. How would we do this? Well, let's start by writing each out term by term. Writing these out term by term gives us the following expression, where we remember that both of these expressions go on infinitely. If we look at the two expressions we have, these just seem like two polynomials, and we know how to multiply two polynomials together. To find the constant term, we multiply both of our constant terms together. This gives us a0 multiplied by b0. Now, to find all our terms with x, we multiply the constant terms by the coefficients with x. This gives us a0 multiplied by b1 plus a1 multiplied by b0. We can then do the same for the coefficient of x squared. To get our terms with x squared in the product, we'll be multiplying the constant terms by the terms of x squared, and we'll also be multiplying the terms with a single x in them together. And we could continue doing this process indefinitely. We can now notice when we were choosing our coefficients to multiply to get the term x squared in our product, we were choosing them so that when we sum their indexes we get 2. And this makes sense because the index of our coefficient is exactly the same as the power of x. Let's now take a closer look at our second term. We could write this as the sum from j equals 0 to 1 of aj multiplied by b1 minus j, all multiplied by x to the first power. And again, this is because we wanted the sum of our indexes to be equal to the power of x. We could do exactly the same for the coefficient of x squared. In fact, we could make a similar sum as the coefficient of any power of x. We can finally write this as a sum over our different powers of x, where each coefficient of our power of x will be equal to one of the coefficients we found earlier. As we discussed earlier, to find the coefficient of x to the nth power, we need to add together the product of all terms whose indexes add to n. And this gives us a motivation of how to multiply two power series together. If we're given two power series which converge for a certain value of x, then the product of these two power series is equal to, we sum over n to find the coefficient of x to the nth power, and this coefficient is the sum over j of aj multiplied by bn minus j. Let's take a look at an example to see how we can use this formula in practice. Multiply the series 1 divided by 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the nth power x to the nth power by itself to construct a series for 1 divided by 1 plus x squared. Write the answer in sigma notation. We recall if we have two power series, f of x is equal to the sum over n of an x to the nth power, and g of x is equal to the sum over n of bn x to the nth power, which both converge. For this value of x, then, we can calculate the product of these two power series, f of x multiplied by g of x, as the sum over n of all of our x to the nth power terms with the coefficient the sum over j, aj multiplied by bn minus j. In our case, we want to multiply 1 divided by 1 plus x by itself to get a power series for 1 divided by 1 plus x squared. So we'll set both of our functions f of x and g of x to be equal to 1 divided by 1 plus x. So we have both f of x and g of x are equal to the sum of 1 over 1 plus x, which are equal to the sum from n equals 0 to infinity of negative 1 to the nth power x to the nth power. So for the value of x where our power series for f of x converges, we can use our formula to find an expression for f of x squared. The question tells us that 1 divided by 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the nth power x to the nth power. This gives us that aj is negative 1 raised to the power of j, and bn minus j is negative 1 raised to the power of n minus j. Therefore, we can calculate aj multiplied by bn minus j as negative 1 to the power of j multiplied by negative 1 to the power of n minus j, which is just negative 1 to the nth power. So we now have our coefficient of x to the power of n is the sum from j equals 0 to n of negative 1 to the nth power. And we can see that our summand, negative 1 to the nth power, is independent of j. So in fact, our sum is negative 1 to the nth power added to itself n plus 1 times. This is because j goes from 0 to n. And if we're adding negative 1 to the nth power to itself n plus 1 times, this is the same as saying n plus 1 multiplied by negative 1 to the nth power. Therefore, we've shown for the values of x where our power series for 1 divided by 1 plus x converges, we can multiply the power series of 1 divided by 1 plus x by itself to get that 1 divided by 1 plus x squared is equal to the sum from n equals 0 to infinity of negative 1 to the nth power multiplied by n plus 1 multiplied by x to the nth power. So, to summarise what we've shown in this video, if we have two power series, the sum from n equals 0 to infinity of anx to the nth power, and the sum from n equals 0 to infinity of bnx to the nth power, which both converge for a particular value of x, then we can add these two power series together to give us the sum from n equals 0 to infinity of an plus bn, all multiplied by x to the nth power. And, in particular, if our first power series has a radius of convergence r1, and our second power series has a radius of convergence r2, then we know we can add the power series in this way for any value of x such that the absolute value of x is less than the smaller of r1 and r2. And for our power series, the sum from n equals 0 to infinity of an plus bn all multiplied by x to the nth power, if we call its radius of convergence r, then the minimum of r1 and r2 gives us a lower bound on r. Finally, we were shown if we were given two power series, the sum from n equals 0 to infinity of anx to the nth power, and the sum from n equals 0 to infinity of bnx to the nth power, which both converge for a value of x, then the product of these two power series is given by, we sum over all of our x to the nth terms, and their coefficient is the sum from j equals 0 to n of aj multiplied by bn minus j.